Welcome. This is Complexity Science. I'm Alan Downey. I've got links up here for the slides and for the software setup. If you had a chance to do that ahead of time, great. If you're working on it, that's okay, although try to pay attention too. And when we get to the first notebook, I will walk through a little bit of the setup. So if you're having problems or anything like that, there will be time later on. It will be okay. So, welcome. Thank you for coming to this tutorial. Welcome to the first day of Scipy, if you didn't do a tutorial this morning. I taught the Bayesian statistics tutorial this morning, so I'm into my 5th hour of standing up here and presenting. I might start to fade a little bit in the afternoon, but I know that many of you have also been attending tutorials all day, so we'll be all right. We'll hang in there. We will take a lot of breaks, and we will get to it. I teach at Olin College, which is outside of Boston. It is a new school, 15 years old. Our mission is to fix engineering education. So if at some point you would like to talk to me about engineering education, let's do that. One of the ways that I'm fixing undergraduate engineering education is by pulling in some topics like Bayesian statistics, which is usually a graduate level topic, and complexity science. So what you're seeing today is partly my undergraduate curriculum in complexity science, which is, here's my definition: complexity science is modeling and simulating complex systems, which is not the most enlightening definition. A complex system is a system composed of components that interact with each other. Also not that interesting a definition. We will refine this as we go along. In complex systems, it's often the interactions that determine how the system behaves. That's the interesting part. That's the thing that is worth studying. So one way to think about this is, in physical systems, sometimes there is one component, and sometimes there are an infinite number of components. And the two endpoints are relatively easy. When there's just one thing, it's simple. When there are a very large number of things, you can aggregate and the average behavior becomes predictable. The middle is where interesting stuff happens. So complex systems is partly the study of systems where there are many, but not infinitely many, components. And historically, there's kind of a progression of science that was primarily about one or two things in the 1600s and 1700s. With things like statistical mechanics, we got into very large numbers of aggregatable, identical things in the 1800s. And it's really only the 20th and 21st century where we started to look at complex systems. And education has a tendency to follow history in that way. So the science that you study in high school is almost entirely 18th century science. You don't get to the 19th or 20th century in high school. If you do college, you get to the 1800s. If you go to grad school, you get to the 1900s. But most people in a standard science curriculum don't hit a lot of complex systems. Now, I'm oversimplifying vastly to the point where I'm practically joking. But as a general statement, there's something there. This is, in my opinion, regrettable because complexity science is a useful thing. It has a lot of implications for what we know and how we know it, epistemology. We're going to talk about that a little bit today. It's also just kind of fun. It's elegant and interesting and fun. And that is my goal for the tutorial, is to show you some of the fun stuff and also talk about some of those implications. We're going to do 3 parts. The first part is about agent-based models. Second part is cellular automata. And then the third part is random graphs. And as I said, some philosophical interludes. Hopefully, 4 hours from now, you will know what complexity science is and have a sense of what it's like, and at least think about how it might be applicable to things that you work on. I'll also have some resources at the end if you want to do more reading. I'll make some recommendations. So first up, agent-based models. One of the resources I'll point you to, this was a nice Economist article recently talking about uses of agent-based modeling in economics, but also in social sciences, and also more broadly in engineering. Don't read that now, but in your ample free time, you might want to take a look at that. So we're going to start with one agent-based model, which is one of the first agent-based models from 1970. So it's pretty old at this point. And it is Schelling's model, Thomas Schelling was an economist, of segregation. And in particular, he was looking at racial segregation in housing, but this is also true for other kinds of political polarization and other systems in which the agents are sorting themselves by following local rules, generally simple rules where each agent looks around at its neighborhood and makes decisions. In particular, the model that Schelling did, there are just two kinds of people, red and blue, and you can make that out to be whatever you want, but if you want to think Democrats and Republicans, feel free. And they live in a rectangular world where everybody lives on a grid with 8 neighbors. And each neighbor kind of looks around to get a sense of, are there other people like me? And they'll have a threshold that says, if, let's say it's 30%. If fewer than 30% of my neighbors are like me, I become unhappy and I move by choosing a random location and jumping to it. Now, you can vary that threshold. This is one of the things we'll do, is to see how does the behavior of the system depend on what that threshold is. And we'll see how all that goes. So we'll jump right in. The first notebook is going to take you to an implementation of this model. If you have done all the setup ahead of time, and you are familiar with Jupyter Notebooks, feel free to just jump in and read the first section, which is called Implementing the Model. If you are unfamiliar with any of these things, I will walk you through a little bit of the setup. So I'm actually going to conda deactivate just to get me to a nice, oops, this is what I want. Sorry, I'm going to move some things around here. That there, put this here, make this bigger. Okay. I'm going to assume that you have downloaded my repository. Again, the links I provided, you can start from there. That'll take you everywhere you need to go to find it. You have my repository. You should be able to CD into complexity science. One of the things that you will find there, you'll find all the notebooks for this workshop, and also environment.yml, which tells Conda all the things you need to install to set this up. So if you want to, you can use a Conda virtual environment to do this. You don't have to. If you just install all the things on that list, let's take a look. If you have all of those things installed, then you don't need to worry about it. The one that you probably don't have, if you have a standard Conda environment, you probably don't have empirical dist at the end, and you can pip install that. Like that. If you don't want to install everything by yourself, the simplest thing to do is to conda env create from a file and use the environment file. And that will create a Conda environment that has everything installed that you need. And I'm not going to run that because I already do, but I'm going to leave that up there for just a second in case anyone needs it. This is one of the things that I've learned in 20 some odd years of teaching, which is the strategic deployment of T. So if I ask a question, people never wait long enough. So I pose a question and then have a sip of tea while I wait. It ends up being a lot of tea. Okay. If you did create a virtual environment, and again, this is optional, but if you did, you can conda activate, and the name of the environment is the same as the name of the directory, complexity science. All right. What my prompt is telling me there now is that I'm in the complexity science environment, that's the parentheses, and I'm in the complexity science directory. And now, if I launch the Jupyter Notebook, it will grab a browser And this, I learned this morning, is a frequent point of confusion about Jupyter, which is that many, many people tried to run Jupyter and then the name of the notebook that they wanted to enter. And that does not work. So if you're not familiar with Jupyter, just a warning, Jupyter Notebook launches the Jupyter server in notebook mode. It will probably grab your browser and bring the home page up in your browser. If it doesn't, the other thing it does when you start the server is it prints the URL where the front end is available. So you can grab that URL and paste it into a browser. But most of the time, it successfully launches the browser. And your first step is to open the first notebook, which is 01_workshop.ipynb. Okay. Feel free, go ahead and read the first section, which is about the Schelling model. If you are making good progress, great. If any of that didn't work, you have one more option, which is that you can run this whole thing on Binder and you don't have to install anything. So to get to that, I suggest start with the repository on GitHub. So this is, and there are links to this, but if you need it, let me know and I can forward you to it. If you scroll down the installation options, these are the instructions I just followed. And if you get to the magic button, you can press the Launch Binder button. If you are not familiar with this service, this is great. If you have a GitHub repository with Python code in it, maybe more than that, I don't know what else they can run, but also Jupyter notebooks, I guess anything in a Jupyter notebook, they will fire up a virtual machine for you, run Jupyter in it, and give you a web interface to it. And it's free. It comes with one drawback, which is this virtual machine is temporary. If you leave it idle for about an hour, it goes poof, and any work that you've done is gone. So it's fine for a workshop like this, but if you do anything in that notebook and you want to keep it, you might need to make a copy or write some notes or whatever. So that's Binder. Okay. Jupyter. One thing you need to know about Jupyter notebooks. So the notebook contains two kinds of cells, text and code. The text cell, if you execute it, you execute cells by hitting Shift Enter or Shift Return. If you execute a text cell, it doesn't do anything. When you execute a code cell, it executes the code. This cell contains all of the import statements that we need. So if I run this and it doesn't complain and doesn't generate any error messages, it means I have everything I need and the rest of the notebook should work. So give that a try. Matt and Stephanie are here to help out if you're having any problems, and I can come around too. Let's see how it all goes. Okay, I'm going to interrupt you for just a minute. You'll have a chance to get back to this notebook. So if you're not done, don't worry about it. I just want to go through some of the code that you just saw, explain some of the features that I'm using there. Out of curiosity, how many people have used NumPy before? Okay, that's good. There might be a couple of features here that I'm using that you've seen, might be some that are new. Hopefully this will be useful to you. So from the verbal description of Schelling's distribution, we're going to make an implementation of it. We're going to take advantage of NumPy arrays. So I said there are two kinds of people, red and blue, and I also need a way to represent empty cells. So I'm going to have three choices, 0, 1, and 2 for empty red and blue. And I'm going to give them probabilities. So this is 10% empty, and the other 90% is split 50-50 between red and blue. Then I'm using np.random.choice to choose from those three values with those probabilities. And I'm going to make an array that's n by n. It's good? Any questions about that? I should take a sip of tea. Okay. D-type, oh, it's in the code but not in my notes. That's telling NumPy that this array should have, is it int 8? Yeah, So it's an 8-bit integer. And I did that because I know that I'm not going to have any values in this array other than 0, 1, and 2. Actually, I'm going to do a little bit of arithmetic. The biggest number I'm going to deal with is 100. So it'll work out. OK. Second thing I'm going to do is display this array using the matplotlib. So I've imported matplotlib as PLT for pyplot. And I'm using imshow, image show, to just represent these values on a color scale. That CMap is a color scale that I created so that 1 looks like red and 2 looks like blue. And let me just see if I've got a picture of that. I don't, but you get the idea. You've seen it. So that's a little bit of matplotlib. Next thing I need to do is some logic to try to figure out which agents are happy and which ones are not. So what I need is for each agent to look around at its neighborhood and count up the cells that are the same. So first step, I'm going to make some logical arrays to just keep track of which cells are red, which are blue, and which are empty. So empty, red, and blue are logic arrays that are true and false, or 0 and 1, however you want to think about it. Now, looking around your neighborhood can be expressed mathematically as a two-dimensional convolution or a two-dimensional correlation. So I'm using the Scipy function correlate2D, and I'm going to explain exactly what that does in a second. I'm going to use a kernel, which is a way of representing the neighborhood. So it's a 3x3 array that is 1 for all the cells that I want to count and 0 for all the cells that I want to ignore. And the way correlation works is that it's going to take that kernel, the 3x3, and it's going to line it up with each cell from the input array and compute the output array. And this animation shows how that works. So each step of the animation, I take my kernel and multiply it by the input and add it up. So this is a way to express the idea of looking around your neighborhood, taking advantage of this built-in library function that is fast, because it's mostly running in C code, and it's really a concise way to express the computation. The only problem is that it requires us to understand convolution, which takes a little bit of thinking about. If you haven't seen it before, this will be confusing, but possibly the most valuable thing you learned today. If you're not familiar with this operation, it turns out to be useful for all kinds of things. So take a minute to digest it. If you have questions about it, let's do that. But let me just do a couple more steps and we'll come back. So I use correlation so that everybody can look around at their neighborhood. Let me just go back here. So if I apply this kernel to the red logic array, then I get for every cell the number of red neighbors, and num blue is for every cell the number of blue neighbors. Now, to figure out who's not happy, I'm going to use the where function. How many people know about the where function in NumPy? Okay, good. About half of the room is about to learn about the where function. This is the second most useful thing you will learn today. The where function is kind of like a parallel if statement being applied to an entire array. It takes 3 parameters, kind of like the ternary operator that says, if this is true, then take A, otherwise take B. Same idea. So this says, where the agent is red, take the number of red agents. Otherwise, take the number of blue agents. What that means is that now every cell will contain the number of neighbors that are the same color as it. Okay? So this is all kind of tricky NumPy stuff. But what it means is that I've implemented Schelling's algorithm in about 3 lines of code that will run fast. And runtime might not be the thing I'm most worried about, but sometimes it is. Yeah, question. Where do the empty cells? In this one, the empty cells count as not the same as you. So this says, in effect, I need to have some number of neighbors that are like me. If I were in a completely empty neighborhood, I would be unhappy. There's another version of this where you would count the fraction of your neighbors rather than the number of neighbors. And in that case, the empty cells would matter. Good, thank you. That's a good question. OK. The next part is relatively straightforward. I'm going to check whether numSame falls below that threshold. So let's say everybody needs 3 neighbors to be happy. I've got 8 neighbors. As long as 3 of them are the same color as me, I'm all right. So I don't mind being outnumbered. I could have 5 neighbors who are different. That's all right. But 6 is too many. Okay. And then I'm going to use this function called lockswhere. And that one I wrote. This is a wrapper for np.nonzero. And it's just a wrapper in order to make the interface a little bit easier to work with. Because non-zero returns the indices of all the places in the array that are non-zero, but it returns it as all of the I indexes and then all of the j indexes. And I want to transpose it so that it is a list of pairs. And that is what lockswhere does. OK. So you were working in the notebook. I interrupted you because I wanted to walk you through that. I want to send you back to the notebook now to look at those functions that I just explained, see if it makes sense, ask questions if it doesn't. Whenever you're ready to go on, you can go on to the next section, and we'll come around and help. So if you're working on the exercise and you're making progress without me, feel free to ignore me, but I'll also show a solution here. Now, because it's the afternoon, I will give you a special option if you want it, which is for any of these exercises, if you do not have the functioning brain cells left to work on the exercise, or you're frustrated, or you're bored, or you just don't want to do it, you have the option to just run the solution notebook. So workshop.ipnb has the questions, and this one has the solutions. I already have it open. If you want, you can also, if there's part of a solution that you want to grab, you can cut and paste. But this first exercise is mostly just taking those pieces that I just explained and putting them together into a function. So let me just walk through what this step function does. During each time step, I'm going to choose one random unhappy person and move them. So I'm going to compute the number of neighbors that are the same. I'm going to figure out who's unhappy, and that's what unhappy locks is, unhappy locations. I'm going to choose one of them at random. That's the source. That's where the person is coming from. And then I'm going to choose a random destination, and then move. And move just means that the source becomes empty, and the destination gets the source color. And that's it. Now, this is not the most efficient implementation because each time step, I compute the entire array and then I move one agent. So this is kind of a slow version. We can optimize it, and I'll point you to the optimized version later. But this one has the virtue of being simple. And if you run it, one of the things that you see is that the level of segregation goes up over time. And from the introduction, this is probably not super surprising. People are unhappy if they are, in some sense, unsegregated. They move, and so on average, even though they move to a random destination, on average, that will tend to make it more segregated over time. And whenever you're ready, you can run the next section, which just runs on a bigger grid. I think it's 50 by 50. and you can see what the progression looks like. The first grid there is totally random, and so the level of segregation is pretty close to 50-50. And as it runs over time, the red neighborhoods get big and coalesce, the blue neighborhoods get big and coalesce. And a substantial fraction of these agents now live in a neighborhood that is all one color. If all of that is working, you should be able to run the animation, which is a nice way to just see visually what's going on. It starts out very random, and as the agents move around, it's almost like making cheese. The sticky parts stick together, the curds lump into curds, the whey gets left behind as whey. Okay, you will have a chance to get back to this notebook. There's an exercise that we're going to do in a couple of minutes. But I want to debrief a little bit on what we've seen so far. So the first thing I want to say is this is pretty much Schelling's punchline. The point of this model for him was to show that even when the threshold is pretty high, you still get very high degrees of segregation. So I set it at 3, which means that if you have 8 neighbors, 3 out of 8 neighbors is 37%, you would be perfectly happy. But when that happens, you actually end up with a total level of segregation that's almost 60%. So even though you would be happy in a mixed neighborhood, you don't get it in this world. You end up with a degree of segregation that is substantially higher than what the agents themselves actually want. And that's, from a complex systems point of view, that's an interesting result. Because if you had agents who want to live in segregated neighborhoods and they end up in segregated neighborhoods, that's unsurprising. But people who want to live in mixed neighborhoods, each individual is making decisions that are consistent with mixed neighborhoods, but they don't get them because the global behavior aggregates their individual decisions in a way that they are not happy with. Yes? Good question. Is there a dimension of time that plays a role in this? So in the model, there are a bunch of things that are unrealistic. And one of them is this sort of discrete time steps where each instant, minute, hour, day, week, who knows, a random unhappy person decides to move and they move to a completely random location. So none of this is a reasonable model of human behavior. And on the face of it, it's not obvious what kind of work we can do with a ridiculously unrealistic model. Particularly coming from physical models, we're kind of used to the idea that realism is a good thing and unrealistic models don't do anything useful. This is a little different from that. And I want to address it partly by talking about explanatory models. What kind of work is Schelling trying to do? He's trying to explain at least one possible reason why segregation can arise. So he's not trying to make predictions. This model is not going to tell us, hey, Detroit in 50 years will have some level of segregation. It's not a predictive model. It's an explanatory model. It's an attempt to answer a why question. So by comparison, let me talk about why are planetary orbits elliptical? I don't know if you've thought about this anytime recently, if you've thought about celestial mechanics, but in a classical mathematical model of the world, we have physical laws, we have continuous mathematics, and that allows us to write something that looks like a proof. So, for example, if you have the law of universal gravitation and you have Newton's laws of motion, you can write a differential equation that describes celestial mechanics, and the solution of that differential equation is an ellipse, which feels very much like I just wrote a proof. I proved something mathematically about the world, except that I didn't. I proved something mathematical about a mathematical model. It is true in the model, and there's really no rational reason to believe that it's true in the world. And in fact, planetary orbits are not ellipses for all kinds of reasons. We left a whole bunch of things out of that model. I think I had a list of them. No, maybe not. So what did we leave out? Let me pose it to you. I'll have a sip of tea. Well, you tell me everything that's wrong with the Keplerian Newtonian model of celestial mechanics that proves that planetary orbits are ellipses. No? Other planets. Yep, other planets, yep. No relativity. Point masses. I ignored radiation and dust and everything else in the world. Right. So I took the real world and I simplified it quite a lot. And that's what this is intended to show. Fundamentally, when we use a model, whether it's a mathematical model or a computational model, to make a claim about the world, we are making an argument by analogy. We're saying that my model is similar to the physical system. I use the model to do some kind of derivation, and in my model, I predict a certain kind of behavior, and I expect the real world to behave like that prediction to the degree that the model is like the real world. Which, if you are familiar with the rules of logic, an argument by analogy is a fallacy. It doesn't actually hold logically. It's just an expectation that we think this has a tendency to work. And we have a couple of 100 years of good science that shows that it does generally work. But it is based on this idea that the model needs to be as similar as possible to the world. And that if the model is unrealistic, then you cannot make this argument by analogy. And Schelling's model is kind of different from that in an interesting way. So this, again, this is just a statement of, if we think the model has captured the important stuff, then we believe that its predictions will be true. We hope. So what is this Schelling model is awful. It's wildly unrealistic in all the ways that I mentioned a minute ago. So what kind of work can we possibly do with the model? One way to think about it is that it is an existence proof. So it's not an argument by analogy. I'm not saying that real cities are similar to Schelling's model. I am making a proof by existence that says it is possible to have a system where we observe high segregation even though people don't like it. So even if the people are really, let's say, mildly xenophobic, they have a mild preference for people like themselves, then we get tons of segregation. So the flip side of that is, if we observe segregation in the real world, a possible explanation for it is lots of individual decisions adding up to that effect, which is meant to be neither an apology nor a solution, but it is a possible explanation. And this is consistent with what we see in a lot of complexity science, which is, if you observe something at the system level, some system level behavior, one way to explain that is to model the components, model their interactions, and see if you can find a set of rules that gets you from individual behavior to aggregate outcomes. So that's the nature of Schelling's model. I'm going to send you back to the notebook in a minute. You can play around with some of the parameters, but then we're going to have an exercise to work on for a little while. And this is based on The Big Sort, which is a book that came out, I think, about 5 years ago. Bill Bishop is a journalist who was looking at segregation by political belief. So Schelling was mostly focused on racial segregation. This is political. And he had a different model. So instead of people get to be unhappy and then they move at random, in his model, oh, sorry, I want a quick aside here. 538 wrote about political segregation a little while ago, and they had a nice article about it. There's a link in the right-hand side there. So feel free to check that out. So Bishop's model is a little different. He said that when people move, they move at random, because that's often true. You have life events that are kind of, you don't necessarily move because your neighbors are Republicans or Democrats. You move because you've got a new job. But then you go looking at houses, and maybe you look in one neighborhood and you see a whole lot of signs for a political candidate, and you think, oh, I don't know about that. And then you go somewhere else, and there are other features that indicate like-minded people, and you go, oh, okay, I'll do that. So we're going to use the same setup as Schelling, but a different process for identifying random people and a different process for choosing their destinations. And you can take all the pieces from Schelling and rearrange them into Bishop's model. And that's what the exercise is. So work on that for a little while, and you can choose your own adventure here. I realize it's the afternoon. So here's my thought. If you want to attempt the exercise, go for it, have fun, don't look at any resources, see if you can do it. If you want to cheat a little bit, you can look at the solutions. And if you are exhausted, you can read either the Economist article or the 538 article and pretend to work. So just type some characters every once in a while. I'll come around and help. We'll resume in a little bit. I'm going to suggest we take our first break. So we'll do breaks roughly each hour if it comes in sort of a natural stopping place. So stretch out, ask me questions if you want to. I think there are snacks out there, or will be soon. There are, thank you. Yes, very good. Go get yourself some coffee. We'll come back, we'll talk about the Bill Bishop problem, and then we'll move on to the next model. All right, I'm going to take advantage of my position here in order to exercise one of my pet peeves, which is buffets. So from a queuing theory point of view, buffets are the worst designed things in the world. And the primary reason, well, actually, there are two reasons. One, if you are ever responsible for a buffet and you put it up against a wall, you should be executed. Because you can immediately double the throughput of the buffet by moving it 3 feet away from a wall. Second, if you are going to get food from a buffet, don't line up. Lining up seems like you are being polite, but it is like a complex system thing where a bunch of people making individual decisions that seem to be polite add up to a system that is actually rude, at least in the sense of being inefficient. Because most of you probably don't want everything from the buffet in order, and when you stand in a line, you are inconveniencing not just yourself, but everybody behind you in line. Proper flow through a buffet is like the way sharks eat whales. You go in, take a bite, get out. Don't stand in line. And yes. What if there's some kind of sequencing in the buffet? Yeah, there might be some details of this model that I need to take into account. Right, you do need the bowl before the soup, I understand. Okay. Getting back to Bishop's model and Schelling's model, here is a solution. It's not the only way to write this code, but it is mostly taking the pieces that we've seen so far and reassembling them. And a couple of people have made some suggestions that say, hey, when you choose a random location to look at, you're not checking for duplicates. It's possible that you are looking at the same house twice. And someone else was suggesting some other ways that this might not be a correct implementation of Bishop's model, but it does, over time, have a tendency to accumulate segregation. And the result, the behavior, is qualitatively similar to shelling. So what I mean by qualitative, it's not quantitatively the same, meaning numerically it produces the same numbers. It is qualitatively the same in that it produces the same kind of behavior. And the kind of behavior is lots of segregation in the world, even though the agents aren't really doing anything to make that happen, other than little nudges, little random nudges toward segregation. And that was one of the things we were talking about in the front here a minute ago. This kind of model tends to be very robust. What I mean by robust is you can do shelling, you can do variations of shelling, you can do bishop, you can do variations of bishop, almost no matter what the rules are. If the agents have any preference, even a mild preference, for people like themselves, and if they make decisions that are guided by that, even if they are mostly random, but just nudged in the direction, then the global behavior tends to be lots of segregation. And that robustness is a feature of the model because it makes us think that this could be one of the things that is happening in the world. I don't want to overstate this result. Neither I nor Schelling nor Bishop are saying that this mechanism is why there is segregation. We're only saying that it is possible for little local decisions to add up to global behavior. And if that only worked with a very carefully calibrated model, then it wouldn't be a very good explanation because we would think that's probably not what's happening in the world. But if we see it happening with an entire category of models, then we start to think, it's seemingly easy for things in the world to behave like this one way or another. And that, I'm going to wrap up my discussion of agent-based models. That is one of the virtues of agent-based models, is this kind of versatility. You can ask what-if questions. Like, what if people applied a slightly different rule? What if people actually had a preference for mixed neighborhoods and they would move if there were too many people like themselves? So you could have a U-shaped curve that says, I'm only happy in the middle, I'm unhappy if nobody is like me, and I'm unhappy if everybody is like me. It's an interesting question. It's the kind of thing we can do with this model. We just have to tweak the rules a little bit. It turns out in that scenario, you still get segregation, even if people actively don't want it. Okay. So let me pause there for a second. We're going to move on to cellular automata. But let me see if you have any thoughts or questions about Schelling or Bishop. Yeah. Good question. So does this only help us with the hypothesis generating part of science? Because it seems like we can't verify anything. Like, how would you contradict Schelling? What kind of data would say, nope, that Schelling explanation is incorrect? That's a really good question. And for this kind of model, I would say yes. For other kinds of agent-based models, they are not just explanatory. They are also predictive. And because they make predictions, they can be contradicted or falsified. So an example of that, we were talking about models of crowd behavior, like buffets. We could do a simulation of this and see whether my protocol is better or worse. And that could be predictive. We could say mine is 30% better, and we could test it. People use this also for planning emergency exits. If you are designing a building and you want to see how long it will take the crowd to get out of a room or out of a plane, you can simulate behavior, and you can have different kinds of agents. You can have some agents that panic, and you can say, well, what happens if 10% of my population panics? There's an interesting paper in this field. Some people have suggested that you can actually improve emergency exit behavior by adding obstructions, which is wildly counterintuitive, but it filters people into paths that are more efficient. So instead of mobbing a door and nobody gets through, it slows people down, kind of like metering lights on highway ramps. By slowing people down, you speed people up. Other ABM questions?
There's actually a qualitative difference between the Schelling and Bishop, which I noticed in learning some of your examples. In the Schelling model, as the threshold increases, the stochastic element overcomes the mild discriminatory preference. And so, in fact, between threshold 4 and 5, the degree of segregation goes down and continues to go down as the increases.
Yes.
Schelling,
Yep. Yes, very interesting.
Makes sense.
Yes.
But I actually think of it until I saw the picture.
That's great, thank you. That's a nice observation. Let me paraphrase it just so people hear. So in the Schelling model, it turns out that as you crank up the threshold, the degree of segregation eventually rolls over and starts to go down again. The problem is that with a very high threshold, everybody is unhappy all the time, and they're moving at random. So at that point, it just becomes random motion, and it doesn't tend to go toward segregation. And your observation is that the Bishop model does not have that problem. The parameter in the Bishop model is how many houses do you look at before you decide to move. And in that case, it levels off at some point because you achieve the maximum amount of segregation that you can have in the system, but it never rolls over and goes down, except maybe just for random variation. Thank you, nice observation. Anything else? Yes?
So, the AgentBased model I have experience with the rule set is significantly more complicated and tends to have a lot of parameters that have to be right? So, as the, what I've experienced is that as these agents have more and more complicated behavior, they kind of tend to go into a unstable. And so, you have thoughts based on experience of how to deal with the fact that as you add more and more complicated rule sets, you know, when you perturb the system or hyperparameter, you know, you sort of land your model's not as
Right, interesting. Okay. Again, let me paraphrase. So your observation is in agent-based models where the rules are more complex, and also probably heterogeneous agents and other, as you add more and more, you're observing that they tend to be less stable. And you might, I think there are two kinds of stable that you could be talking about, stability and time. So these models have a tendency to level off. They don't, you know, behave chaotically over time. But you were talking about sensitivity to parameters, that they are unstable in the sense of I make a tiny change and the behavior of the system is wildly different. I'm not sure I could make that a generalization that complex rules necessarily go with that kind of instability, but it is very much the case that these models can show all of these behaviors. So they can be stable in time and robust when you tweak the parameters, or chaotic in time and stable when you tweak the parameters and so on. So all four of those quadrants are occupied, and sometimes that's what you want. Sometimes the thing that you're trying to explain is chaotic behavior in the world, and you might think when you see chaos that there must be something complicated going on, and one of the things, a general result from complexity is that in fact you can write very simple universes and very simple rules and see chaotic behavior come out of it. So I'm taking your question and kind of going in a slightly different direction, but that's another example where you can work backwards, making an argument by an existence proof that says just because I see complexity in the world doesn't mean that the underlying behavior is complex. It could be very simple things yielding complex behavior. And in fact, that's a theme of Wolfram's book, New Kind of Science. And that's our next topic, which is cellular automata. So let me jump into that. See, I kind of took that, made it into a segue. Does anybody recognize this cellular automaton? Yes. That is Conway's Game of Life, and that is our next topic. So let's get into that. John Conway is a mathematician who invented Game of Life in 1970 and regretted it ever since because it's the thing that he has become most famous for. So he kind of loves it and kind of hates it. Martin Gardner wrote about it in Scientific American, and then it just took off. People loved it. The general, the setup is similar to Schelling's model. So we've got a grid, rectangular grid, everybody has 8 neighbors. There are 2 kinds of cells that are kind of abstractly alive and dead. Now, these designations don't really mean much. This is not meant to be a model of biological systems. It's more abstract than that. But if you think of cells as being alive and dead, each cell counts up the number of neighbors who are alive and then applies a set of rules. Those are them. I'm not going to read these to you. You can read them. Let me just say, there's a set of rules, and you'll have a chance to digest them in a minute. Let's get into the notebook. I have to make a small correction in the notebook for it to work correctly. So stay with me for just a second. Follow along. We will make a fix, and then you'll be ready to go. So open up O2 Workshop. And run the first few cells. And then when you get to here, this cell has the class that is the game of life. And I had an experiment that I did. Oh, maybe I think I already fixed mine. Bear with me for just a second. Egad, I've made a mess of it. I think it is. Maybe not. Okay. In the step function, you'll see that we're using correlate 2D again. I'm going to give you a chance to work with the notebook a little bit, and then I'll explain how this implementation works. I believe that you will find in your notebook, it has boundary equals wrap, which causes the boundary conditions to wrap around. For this notebook, that's not what we want. I was playing around with it and accidentally saved the incorrect version. So if you just remove that, in fact, if you just search for the word boundary and delete that argument, then everything else in the notebook should work. So take a minute to work through it and do the first exercise, and then we will resume. So if you start the game of life with a random configuration, it has a tendency to run for a while with this behavior that kind of looks like fire spreading around. And what it leaves behind are a number of different configurations that tend to appear spontaneously. And people who have too much time on their hands have named these configurations. So some of them are called still lifes because they're like a photograph that doesn't move. So these are stable configurations in the sense that when you apply the rules, it's the same in the next time step. So a 2x2 block is called a block. And if you count, each of those live cells has 3 neighbors, which means that it stays alive. And all of the dead cells have fewer than 3 neighbors, so none of them come to life, and so it doesn't move. Similarly, beehive, loaf, boat, tub, these are all unchanged by applying the time step rules. The other patterns are called oscillators, which is that they do change from time step to time step, but after some number of time steps, they come back to their original configuration. And the period 2 blinker is one of the ones that appears the most commonly spontaneously. Some of these others, like the pulsar and the pentadecathlon and things like that, don't show up very often when you start from a random configuration. People have designed them. And in fact, there are a lot of really complex configurations that people have designed for a really hard kind of design. If you think about this from an engineering point of view, when we design engineered systems, the primary tool that we have to use is isolation of subsystems. You take a big complicated thing, you break it down into sub-problems, and you define a clean interface between them so that if this works and that works, and you put it together, it will work. Game of Life defies that kind of design. Because if you take, for example, 2 still lifes and put them together, it's not a still life anymore. And you're going to get nearly entirely unpredictable behavior. So this is a universe where trying to design something that has a particular behavior is all but impossible. I'll come back to that in a minute. One of the other features of this system is what are called gliders. They are similar to oscillators in the sense that after a certain period, they come back to their initial state, but that initial state has been translated in space. So the glider, for example, takes 4 steps. After 4 steps, it's back to its original shape, but it has moved 1 cell along a diagonal. And similarly, there are a few other spaceships that move at different speeds and different directions. Now, one thing to think about when you think about Game of Life is these moving objects are kind of weird because they don't really move. In the Schelling model, the agents actually move. I take the state from one part and I move it to another part. That is not happening in Game of Life. There are no non-local interactions in Game of Life. And in fact, there's not even any motion. The cells just blink on and off. They don't move at all. So in some sense, that motion is an illusion. And in some sense, spaceships don't exist. They are not a thing. They are an epiphenomenon that comes from the interaction of the rules over time. And that might seem like a kind of a satisfactory thing. Okay, spaceships don't exist. It's kind of like marquee lights when you see the light bulbs moving around on an electric sign, right? They're not really moving, they're just blinking on and off. The movement is an illusion created by our perceptual system. Or is it? Because once you accept that notion that these things blinking on and off don't exist, you kind of end up throwing away a lot of things that we think do exist. This is actually an old philosophical question. It has a name. It's called the ship of Theseus problem. And it comes from a thought experiment that says if the original ship built by Theseus, over time, things break and they get replaced. At some point, if you have replaced every single component of that ship, in what sense is it Theseus's ship? And this is a question that people have been asking so long that they asked it in Greek. So this is Heraclitus asking, we both step and do not step in the same rivers, we are and are not. And you have probably heard a version of this. You might have heard, you never step in the same river twice. And the sense of that is, a river is kind of like a glider in Game of Life. It's not made up of the same water over time. It's not in the same place over time. So in what sense is it the same river? And Heraclitus was not really talking about rivers. He was talking about everything, because everything changes over time. So none of the cells in your body right now are original equipment. You are the ship of Theseus. You have been replaced many times over. So in what sense, if any, are you you? Now, I'm not going to attempt to answer that question. This is an example of what I call the black hole of complexity science, which is that all of these examples will eventually lead you to a philosophical black hole, kind of like Wikipedia. And do people know about the philosophy hypothesis on Wikipedia? This is not originally from XKCD, but it was popularized by XKCD. The thesis is, if you start on any Wikipedia page and you click the first link and repeat that process, you will eventually end up on the philosophy page. Now, the first link we have to be a little bit careful because there are sort of utility links and there are links that are in parentheses and stuff like that. So you have to ignore that. It has to be the first substantive link. So here's what I would like you all to do. Pick a random page on Wikipedia, play this game, and in a couple of minutes, tell me how many clicks it took, or if you don't get to philosophy, tell me that. All right, so complexity science is a philosophy black hole. It is also a tangent. Okay, if you would go back to the notebook, you can read through the section that is called Methuselah's, and then when you are ready, there is an initial configuration called rabbits that multiplies like rabbits, hence the name, and you can run it on the command line. So we'll take our second break in about 10 minutes, but we'll also move along. I'll nudge you, and then you go. You can also kind of take this where you want to go. So spend your time where you want to spend it. I'll talk just a little bit about Methuselah's. One of the things interesting here is that you can start with a remarkably simple initial configuration. So the R pentomino is only 5 live cells. Rabbits, if I remember right, is 9. And they go for thousands of time steps before they eventually converge to something that is stable. And by stable, what I mean is they might be going through a periodic repetition pattern, but the number of live cells is bounded. So even if you've got oscillators, the number of live cells might go up and down a little bit over time, but there will be some upper limit that it won't exceed, so it's bounded. And this is a question that somebody asked is there any initial configuration that evolves in time so that the number of live cells is unbounded? It continues to grow indefinitely. And that was Conway's conjecture. So when he was working on Game of Life, he conjectured that the answer was no, but he kind of did it as a challenge. I don't think he believed that the answer was no. He has said that he hoped that the answer was yes, but he wanted to throw the conjecture out as a challenge, and if I remember right, he offered a $50 prize to whoever could come up with the first initial configuration where the number of live cells would grow unboundedly. And you can think a little bit about how that could possibly work. There are 2 strategies that people thought about. One is called a puffer train, and the other is called a gun. So a gun is something that sits there without moving through space, and it goes through a periodic pattern, but each period it produces one spaceship or more, each period produces some number of spaceships that go out, and on an infinite grid, they'll just keep going. And if you're producing more and more spaceships over time, total number of live cells increases. And then the other possibility is a spaceship that moves through space and leaves behind detritus. And either way, you get infinite behavior. Now, both of those things turn out to exist. The first example that contradicted Conway's conjecture was Gosper's gun, Gosper's glider gun. So this is the initial configuration. There's what it looks like as a representation. Obviously, not obvious how this works. Not obvious how you design something like this. But if we animate it, when you watch it run, you can start to get a sense of how things work in Game of Life world. Yeah. So there are actually 2 spaceships there that are going back and forth. The 2 spaceships are doing this. And what he discovered is that when a spaceship hits a block, it reflects. And when two spaceships hit each other, they produce a glider and change direction. But they have to hit each other in the right phase, and they have to hit each other in the right alignment, or it doesn't work. And you can imagine trying to design something like this. But this was the original thing that grows unboundedly. Now, in my example, my boundary there isn't quite right, so my gliders are interacting with the boundary, but ignore that. On an infinite grid, they keep growing forever. Yeah?
Was this visually determined, trial and error, or did the grad student actually figure this out mathematically?
Did the grad student actually figure out mathematically? There's not really any math to figure out here. It's partly trial and error, in the sense that you can try, two gliders like this, and then two gliders like that, and two gliders that are out of phase like that, and so on, or two spaceships. But once you've identified some of the entities, you can enumerate all the pairwise interactions and see how they behave, and then start to build up from there. So it's not an impossible world to do engineering in, but it's a pretty difficult world to do engineering in. And a lot of it gets done by brute force, by searching through large spaces of possible interactions, but that's what computers are good at. So that's Gosper's gun. And the other one that you can take a look at is called lifepuffer.py. You can run it from the command line. So Python life. This is the puffer train. And this is two spaceships running in parallel, and then the space between them has a tendency to accumulate stuff, and they leave this pattern behind them. And the pattern actually grows quite a lot, but the pattern never catches up with the spaceships to mess up the spaceships. And we know that for an interesting reason, which is that in Game of Life world, there's a speed of light. Because each cell can only interact with its neighbor during one time step. So nothing in Game of Life can move faster than one cell per time step. And so once you have a sufficient head start on something, it can't catch up with you. This, by the way, is intended to demonstrate one other thing, which is that this is all run in NumPy. My implementation of Game of Life is basically 3 lines of NumPy. And I'm going to show you that implementation in a second. As a result, it runs pretty fast. This is, I think, 1,000 by 1,400, and it's doing several updates per second on a not very fast computer. So this example is one of my answers to the question, is Python slow? And the answer is, if you write things like NumPy, it's about the same speed as C. So my comeback is C too slow? By far the most expensive part of this update is drawing it on the screen. If all I wanted to do was the updates, it would be much faster. Let me close that before the spaceship goes off the screen. And let's talk a little bit about the implementation, and then we will take our second break. Yes, question.
In your theory, Gosper's gun does not have the velocity.
Really? You end up?
Mathematics loop, yeah.
Oh, very interesting. Good to know. Thank you. Okay, so I mentioned Gosper and his $50 and his gun. We ran LifePuffer. Let's talk about the implementation. What am I going to use? I'm going to use convolution, because this is awful. This is the brute force implementation of Game of Life, where I use array slices to pull out 3x3 arrays, and then my rules are basically if statements. I've just taken Game of Life rules and translated them into if statements. And this works, but it's slow and it's not such great code. Here's an alternative. I'm going to use convolution. I'm going to use the same kernel we used for Schelling's model to count the neighbors. So this is going to count the number of live cells. And then the rules say that you will be alive during the next time step if either you have exactly 3 neighbors or you are alive and you have 2 neighbors. And that is that. I'm going to make one more change to this, but let me pause and see if this makes sense, because I'm about to tweak it. A means you are currently alive. A is the array that contains the zeros and ones for being alive or dead. Thank you, I should have said that. All right. Now, so this kernel is all zeros and ones, which means that I either add in a neighbor or I don't add in a neighbor. But you can also put other numbers into a kernel, like 10, for example. If it's 10, what that means is that you get 10 points for the middle cell plus 1 point for each of your neighbors. So if you're dead, you don't get the middle cell, and your neighbors are 0 through 8. If you're alive, you get 10 points plus 0 through 8. So that means that every neighborhood is going to map onto a number that's either 0 through 8 or 10 through 18. And that number tells me simultaneously, am I alive and how many neighbors do I have? And now the magic numbers are 3, 12, and 13. And I can do one step even better, because when I do all those logic arrays, I'm actually creating arrays. So I'm doing a lot of memory allocation. It would be better to do this as a table lookup. So I'm going to create an array of 20 zeros, and I'm going to put ones in it for the magic numbers. So 3, 12, and 13 will be 1. And now I can do an entire step in Game of Life by doing 1 correlate and 1 table lookup. Because I can save the table, I don't have to compute that every time. And I can save the kernel, I don't have to do that every time. So that's a Game of Life in 2 lines of code and only 1 copy of the array. Yes. 20, well, my numbers go 0 to 18, and I left a little room just in case. I could have been more efficient. The middle cell could be worth 9, and then it would be a little bit more compact, but. Questions about this implementation? So this is a little bit of gratuitous NumPy hackery, but it's kind of a useful set of tricks to have in your toolkit. Hopefully it's useful. All right. So save this example if anyone ever tells you that Python is too slow. When we come back, we'll take our second break. When we come back, we're going to implement, there are different rules for Game of Life. And one variation is called High Life. And it adds one more rule. The magic numbers are 2, 12, 13, and 6. So we'll add one more magic number and see how the world behaves. We'll come back at 3:35. So as you're exploring different rules, what you'll find is that there are a couple of different behaviors that you see. If you make a world where it is easy to stay alive and easy to become alive, so lots of rules, then you tend to see the kinds of things that we were just looking at, where it obviously grows in an unbounded way. And they are cool patterns in the sense that they're pretty. They often look like Oriental rugs. But they're not complex patterns. They have a simple recursive structure that generates them. The other kind of world that you get is the kind of world where it's really hard to stay alive. So if we say, okay, you need exactly 3 cells to stay alive, and that's the only way, what we're probably going to get is extinction in a short period of time. yeah, poof. So there are kind of like three kinds of worlds. There are the ones that just disappear instantly. There are the ones that grow unboundedly. And then there are the ones that are on that boundary where it's not too hard to live and not too easy to live. That's where the interesting stuff happens. That's where Game of Life is. And Game of Life turns out to be not just interesting in the sense that we can make a Gosper gun and all that, but also interesting in the sense that we can do computations with it. Turns out that if you take a bunch of these gliders and make them interact with each other, you can have two gliders that will only produce a glider if they're both present, or that will produce a glider if either of them is present, or you can make a NOR gate, and once you have a NOR gate, as you might know, you now have the ability to do arbitrary computation. And it turns out that Game of Life is in fact Turing complete. Any function that can be computed by a Game of Life cellular automata by having spaceships crash into each other and basically execute logic. And this is the basis. Let me see where I was headed with this. Yes. I say this in slightly not quite in order. So this is an example of one of the themes in complexity science, which is called edge of chaos. And it's the idea that very often there are parameters that you can tune, like the rules in Game of Life. And if you turn the knob all the way in one direction, you get simple, uninteresting. All the way the other, simple and uninteresting. And the middle is where interesting things happen, where complexity is maximal. And let me say a little bit about what that can mean, because all of this is a little bit vague in places. I want to talk a little bit about one of Wolfram's ideas in his book, which he calls the principle of computational equivalence. And what it says is that all of these different systems that do computation compute the same set of stuff, which sounds a lot like the Church-Turing thesis. If you're familiar with it, it says that there is a set of computable functions, and by and large, anything that can compute at all computes exactly that set, which is kind of weird and kind of surprising. We now have lots of different examples of systems that can do computation, and the fact that they turn out to be equivalent is surprising and interesting. Wolfram's additional claim is that this is also a property of the world, that in natural systems, it is often the case that natural systems can do a kind of computation, and when they can, they compute exactly the same stuff, the set of computable functions, and that's his principle of computational equivalence. It's a little bit of a weird claim. It is not what you would say is universally accepted by people who are not Wolfram, but it's an idea that comes out of these cellular automata. I wanted to bring it to your attention. So read more about that if you like. The other theme that we're seeing here is what's called emergence. And this is the idea that you can have simple rules at the low level that yield complex behavior at the high level, and that the emergent behavior that you see is A, not predictable for some notion of predictable, and not explainable for some notion of explainable by the low-level rules. I'm going to kind of just leave that hanging because there's a lot there, but if you want to read more about it, Emergent Universe is a nice place to explore. And then the other thing which I mentioned is it is a recurring theme that you can get complex behavior from simple rules, which implies that if you are observing complex behavior, you don't necessarily have to look for complex explanations. That you might be able to find a simple set of rules that is at least qualitatively like what you're observing, and maybe even quantitatively like predictive. Let me pause there. Thoughts or questions about cellular automata?
Why was it called high life?
Why was it called high life? I don't know. Lots of different versions of life have been given names, but I can't explain that particular one. Yes?
Way or examples of discovering these simple rules by looking at complexity?
Good question. So are there examples where we've seen something in the world that bears explaining and we have discovered the simple rules that generate it? Yes and no. So let me give an example and then explain why I'm hedging. So self-organized criticality is one example where we might have an explanation of what happens in the world. So the thing in the world that we observe is long-tailed distributions. So one example is earthquakes. If you look at the power of earthquakes, you get lots and lots of low-power earthquakes and a very small number of very powerful earthquakes. And if you plot power versus frequency on a log-log scale, you see a remarkably straight line. And that is true for earthquakes. It's true for the sizes of cities. It's true for the sizes of craters on the moon. It's true for distributions of many, many quantities in the natural world. It's kind of like the second distribution after the normal distribution. If you add up a whole bunch of things, you tend to get Gaussian distributions, normal, bell curve shaped distributions. So when we see a bell curve, we naturally ask, what's being added up that might explain that? If you see a log normal distribution, that comes from multiplying things together. So if you see a log normal distribution, you might think, what's being multiplied that might explain that? And when you see a Pareto distribution, that's the Richter law and Zipf's law. When you see that, you start to think, what might be some simple rules that would add up to that long-tailed distribution? And self-organized criticality is a potential explanation for that. I'm going to point you to my book, Think Complexity, and I've got a chapter about self-organized criticality. We're not going to do it today, but you can check that out. I had one other thought about that. Let me see if I can remember it. I'll take a strategic sip of coffee. So my favorite example of explaining a normal distribution and a log normal distribution, if you look at the distribution of birth weights, at birth, it's a nice Gaussian distribution. Symmetric, the tails are a little funny, but the middle part of that distribution is a nice bell curve. If you look at adult weights, it is not a Gaussian distribution. It is log normal. It is skewed to the right. My hypothesis, which is mine, is that your weight as an adult is the product of your percentage weight gain for every year of your adult life. And the percent gain is a percentage rather than an absolute. That is to say, people don't gain an ounce a year, they gain 1% a year. So the weight that you observe at a point of time is the product of a bunch of different factors, and the product of independent random variables follows a log normal distribution. So that's an example of, it's a very abstract model. I don't think anybody sets out to gain or lose 1% of their body weight, but descriptively that seems to be what happens. Okay. We have done agent-based models, we have done cellular automata. Our third and final topic is random graphs. So let's get into that. My motivating question for this is the question, are you popular? The answer is no, and I'll explain why. Actually, John Allen Paulos explained why. This is an article from Scientific American from 2011 looking at social networks. And the observation, we're going to use Facebook as an example, but this is true of online social networks and real-life social networks, which is if I pick a person at random, so if I pick you, and then I go to your social network and I pick one of your friends at random, the probability is about 80% that your friend is more popular than you, which is a weirdly paradoxical thing because it seems like I just chose two people. Why would the second one always be more popular than the first, or at least probabilistically? But if you think about it, I went through a different process. When I chose you, and if you don't mind if I continue to use you as my example, when I chose you, every person in the room was equally likely. When I chose one of your friends, they were not all equally likely because the chance that I land on someone else in the room is proportional to the number of friends that you have. And because I have disproportionately chosen people with a lot of friends, they tend to be more popular than the person I started with. That's the basis of that. So to understand this, we're going to do a little bit of work with graphs, and we're going to do a little bit of work with distributions. So in the same way that we played with NumPy a bit, you got a chance to learn about that. We'll do a little bit of NetworkX and a little bit of probability mass functions. Out of curiosity, how many people have used NetworkX? Okay, if you haven't, you get to learn something. And then I'm going to pretty much guarantee that none of you have used this library called empirical dist because I wrote it. It's my tool that I just use for working with distributions. I will explain both of these as we go along. So first part is graphs. I'm going to go through this kind of quickly. I imagine many of you have seen this before, but if you haven't, I'll tell you what you need to know. We're going to use a graph to represent a social network. So each node, which is a red circle, represents a person, and each line represents a relationship between those people. So if two dots are connected, that means they're friends with each other. If they are not connected, it means they are not friends with each other. The crucial number that we're going to talk about is the degree of a node. The degree of a node is the number of edges, and so in a social network, that means the number of friends. And we're going to talk about the degree distribution. So that is across the population, I'm going to count the number of people who have one friend and the number of people who have two friends and so on. So in this graph, I have one person who has three friends and three people who each have one friend. And the degree distribution looks like that. That's three people who have one friend and one person who has three friends. Making sense so far? Is that good? Okay. So let's jump into the third notebook, o3workshop.ipynb, and run the first section, which is called graphs, and do the first exercise. Okay, so part of this is just learning how to use NetworkX. Adding an edge to a graph is kind of easy. And in fact, you can add a node explicitly, or if you just add an edge, and if that edge involves a node that doesn't exist yet, NetworkX figures it out, and it adds another edge. And then the other tool here is the PMF object. So given a sequence, so I'm using degrees to compute the degree of each node in this network, and then I make a PMF. The PMF is a map from each degree to its frequency, or probability, if you want to think of it that way. So in that graph that I just constructed, oh, that's cool. Just coincidentally turned out I made that graph at random, and it has an equal number of nodes that have 1, 2, and 3 neighbors. But it turns out that this is not what social networks look like. This is the egalitarian world, where, okay, no, I take it back. There's a little bit of variability here. Some people are a little bit lonely. Some people are a little bit popular. That's not what real social networks look like. This is a data set that was collected in, I forget what year, but the early history of Facebook. It was made available as an academic data set by the nice people at Stanford, and it is a sample of 4,000 people on Facebook. I think it's a little bit bigger now, but this is at least a small social network. And we can do the experiment that Paulos described, which is to pick a random person and look at the distribution of degree, and then pick a random friend and look at the distribution of degree. And this is what they look like. And tell you what, I actually want to let me just see if there's anything else I wanted to say about the first exercise. Right. Yeah, I'll send you back into the notebook. Why don't you work through that? And when you get to the power law distribution, we'll stop. Let me interrupt you for a second. I realize that I've done a poor job of explaining the PMF and CDF objects. So let me back up just a little bit. So this is the library that I mentioned, Empirical Dist. It provides these 4 classes, PMF, CDF, and then 2 that we are not going to use today. If you ever find yourself doing survival analysis, you might find these other 2 useful. For us, we care about the PMF, which is the probability mass function, and it is a way of describing a distribution like this. It is a mapping from the possible values, which in this case is number of friends, to a frequency, which is the number of people who have that number of friends. So in the Facebook data set, the PMF looks like this. This is the degree distribution for the 4,000 people in the data set. And what it says is that most people have a number of friends that is between 0 and 20, because this function is the highest for a small number of friends. But there are a few people who have 50 friends, there are a smaller number who have 100, and then way out on the tail, there are a few people who have 200, 250 friends. And so when I say popular, I'm talking about people who in this network have a lot of friends. Doesn't necessarily mean very much. Who knows what that relationship actually is? So put quotation marks on popular. But this is the distribution of the number of friends. Now, you'll notice that it's kind of a noisy graph and it's a little bit hard to work with. So I'm going to make the recommendation that we switch from a PMF to a CDF. And here's my question. How many people are familiar with the cumulative distribution function? All right. If you only learn one thing today, the CDF will be the most valuable thing you learn. This is a very nice way for looking at these kinds of distributions. It is nothing other than the cumulative sum of this. So it is the total number of people who have fewer than X friends for each value of X. And this is telling me, for example, that the median, if I find where this line crosses 50%, my vertical axis is percent, the median looks like it's about 20. And the extreme value is 250. And the steepness tells me that a lot of people are in the low numbers and a small number of people are in the high numbers. The CDF is particularly useful for comparing 2 distributions, which is the next thing that comes up in the notebook. So this CDF is what we get if we choose a random person from the population. So everybody is equally likely to be chosen. And this distribution is what I'm going to call the friends of friends. And that's if I choose a person and then choose one of their friends at random, popular people get oversampled. And so I would get the impression that people have more friends. And if I compare them, it looks like this. The blue CDF is, in some sense, the actual distribution of friends. And the orange one is the skewed view of the world that I would get if I sample friends of friends, because popular people get oversampled. In this data set, it's a little bit less severe. It's only about 66% compared to the other number from the article that was 80%. But the idea is the same. We're taking a representative sample and we're comparing it to a biased sample. And in particular, the biasing is proportional to the thing I'm measuring. That each person is being oversampled by a factor of x, where x is the number of friends that they have. And this is an example of what's called the inspection paradox. And this happens a lot. So, for example, if I ask you all, how many children does your mother have? How many biological children does your mother have? And I take the average. That average will be substantially higher than the average fertility of your mother's. The reason is that I'm oversampling large families. If your mother had a lot of children, the probability is high that one of them is in this room. If your mother had no children, the chance is 0 that you would be represented. And in fact, you would be families because of how I just did that sampling, families would be overrepresented in proportional to the number of children. Another example of this is class sizes. So if you ask the dean of a college, how big is the average class size? They might say 25. If I sample all the classes and take the average size, it's 25. Choose a student at random and ask them how big their classes are, the average will be substantially higher because you are much more likely to sample a student in a large class than a student in a small class. So neither of them is lying, they're just averaging over a different sample. This is the family example that I just mentioned. If you get a chance, read that article, not now, but in the future. This is one of those things where once you become aware of the inspection paradox, you will see it everywhere. How many people were on a really crowded plane when you came here? How many people were on a plane that had nobody on it? So people complain all the time because flights are crowded. Airlines complain all the time because their flights are nearly empty. Who's lying? The airlines. But other than that, no, I mean, nobody's lying. They're averaging over a different sample. Overfull planes are oversampled. All right. Now, that's part of it. Oversampling is part of it. The other part of it is this effect becomes more and more severe as the distribution has a longer and longer tail. And that brings us to the second part of this topic, which is about power laws and scale-free networks. So let me introduce that, and then we'll get back into the notebook. So first, I want to talk about different functional shapes for distributions. So if the probability, the PMF, as a function of x is k, it's a constant, it doesn't depend on x, that's a uniform distribution. Okay. What if it's proportional to e to the minus x? So the probability of x is proportional to e to the minus x. What's that distribution called? That's the exponential distribution. Okay. What if it's proportional to e to the minus x squared? What's that distribution called? That's the Gaussian distribution. And what if it's proportional to x raised to a power? In particular, it's a negative power. What if it's proportional to 1 over x to the alpha? What's that distribution called? That's the Pareto or power law distribution. And that's the one we're going to talk about. Now, power law distributions are weird. Pareto distributions are weird. All of your intuition for how probability works is out the window with Pareto distributions. Among other things, you can't compute the mean. Pareto distributions don't have a defined mean. And there's no sense of normal in Pareto world. So my example of this is the distribution of human height. So the average person is, let's say, 170 centimeters. And the standard deviation is 8 centimeters. But there's no adult in the world who is 10 centimeters tall and there is no adult in the world who is 4 meters tall. So what that says is that the distribution has a scale. It has a kind of a natural scale that is on the order of 100 centimeters. In Pareto world, that's not true. There is no normal height in Pareto world. So I can create a Pareto distribution that has the same median as human height. Let's call it 100 centimeters, just to round off. So if it's a Pareto distribution with the median of 100 centimeters, how tall is the tallest person in Pareto world? So let's say you choose 7 billion people from a Pareto distribution with median 1 meter. How tall is the tallest person? The answer is about 100 kilometers. That's what scale-free networks mean. There's no natural scale. All scales show up, not with all the same frequency. What in Pareto world, almost everybody is shorter than 1 centimeter, and there are a few people walking around who are 100 kilometers tall. Now, obviously, the distribution of human height isn't like that, but there is another distribution that is like that. What human property follows a Pareto distribution? Wealth. The large majority of people have 0 or negative wealth, and a few people are walking around who are 100 kilometers tall. Okay, let's get back to the notebook and run the next section, which is about power law distributions. Okay, I want to talk about zip distributions, and I pulled a little bit of a bait and switch because I talked about Pareto, and then the notebook talks about zip. Pareto is continuous, so if you're talking about something like human height, which can take any value, that's continuous, that's Pareto. If you're talking about something like a count, like the number of friends, you can't have 1.5 friends. That's discrete, and so the zip distribution is the discrete version. Pareto is continuous, but mathematically they have many of the same properties, especially this extremely long tail, where many, many people are close to 0 and a few people are way out there at super high values. Now, these distributions are so weird you can't even look at them. Because if you plot Pareto or zip on linear axes, all the data gets mashed up against the lines, and you can't even see what the shape of the distribution is. Now, many of you, if you've been working with long-tail distributions, you probably know, oh yeah, no problem, just put it under a log transform. So set the x-axis to a log scale, and everything will be fine. And actually, zip distributions are too extreme even for that. It helps a little bit, at least now I can see the distribution, but I can't really see the shape of this distribution clearly. But it turns out mathematically that if you put this on a log scale, you get a straight line. And that is, in fact, one of the best ways to test if you have a data set and you wonder whether it's Pareto or zip. One of the ways to test is to plot the distribution on a log scale, and if you see a straight line, that's pretty good evidence. Now, it'll be noisy, and especially out in the tails where the probabilities are low, it can be hard to see exactly what's going on. But if you squint at this and you see a straight line, that is some evidence that it is a zip distribution. Now, this is a synthetic data set. I generated data from a zip distribution, and then I tested it to see whether it's from a zip distribution, and it is. Great. Let's do it with data now. This is from a paper from 1999, Barabasi and Albert. This is one of the first papers to talk about this behavior in naturally occurring networks. And they looked at 3 networks. The actor collaboration graph is who has been in a movie with who. So it's not that 2 actors have to be friends. It's 2 actors are connected if they've been in a movie together. And some actors are not very connected at all. So I think Spalding Gray, I was going to say, at least some of his movies were monologues. So he wasn't in them with anybody. He had no collaborators. But he also did some other movies. But So that's an example of someone who might have a low collaboration degree. And Kevin Bacon is sort of famous for having been in a lot of movies with everybody, so he would have a very high degree. And the distribution kind of looks like there's a bit of a straight line there. Not over the whole range, but maybe part of it. Hard to say. B is the World Wide Web. As of 1999, there were 300,000 pages on the World Wide Web. I think it's bigger now. But that's what the distribution of links looked like. So many pages had a small number of links to them, and some pages had a large number of links, and the distribution follows a straight line. And the third one is the electrical power grid. That a node in this would be either a power generating station or a transfer station of some kind. And many of them are weakly connected, meaning only a couple of connections, but there are hubs that have a large number of connections, and it follows what looks like a straight line. And social networks. This is that same Facebook data that we were looking at a minute ago. Straight line? Ish. So maybe this doesn't apply. So 10 to the 1 is 10 friends or fewer. So to the left of 10 friends, it doesn't seem like it applies. But to the right, there's a line over about an order of magnitude, and then maybe it tails off. It's a little hard to tell. So here's one way of thinking about the popularity paradox, which is there are two reasons you are unpopular. And well, one is that you're at Scipy. But maybe that's evidence rather than a cause. But no, sorry, I shouldn't say things like that. So biased sampling is one. So the popularity paradox is partly because of biased sampling and partly because of this long-tailed distribution. So we could argue about whether this is a Pareto curve or a zip curve. Maybe it's not. But at the very least, it is long-tailed. Many people have a small number of friends and a few people have a very large number of friends. And that's enough to explain the popularity paradox. But the Barabasi-Albert paper goes one step farther and it asks, why do social networks and these other networks have this shape? And this gets back to the question I think I was asked from somebody over here, which was, do we have any explanations for this? When we see Pareto, can we explain where that's coming from in the same way that we can explain normal and log normal? And that's what Barabasi and Albert proposed. Here is their model. It's called the BA model for Barabasi and Albert. They grow a network. Ooh, sorry, I forgot. We're going to take a break. So when we come back in 10 minutes, I will tell you the Barabasi and Albert model. We'll be back at 4:37. Okay, somebody was asking me a little bit about, does complexity science tell us anything about systems that have human beings interacting with each other? And are they predictive? Are they useful? One example that I mentioned is normal accident theory, which is partly looking at human beings operating complex, and in this sense, I mean the ordinary complicated systems. And one example of that is nuclear energy plants, power plants. And Charles Perrow wrote this book called Normal Accidents, which is about exactly that, how we can both explain and hopefully avoid catastrophic accidents by understanding how the humans as part of a complex system interact and cause accidents either to escalate and become worse or get identified and corrected. I'm going to just leave that as a quick mention for now. So we've partly explained the popularity paradox by saying that the distribution of degree in social networks is long-tailed. Barabasi and Albert propose a possible explanation for why networks have that structure. And the two components that you need are growth and growth. So we're going to start with a small number of nodes and add one at a time. And the other aspect is preferential attachment, which is every time I add a new node to the network, I'm going to attach it to an existing node, and I'm going to use the friends of friends algorithm. I'm going to be more likely to attach to a popular node than an unpopular node. And those two aspects, sort of organic growth plus preferential attachment. Preferential in this case means in proportion to popularity. If you have those two things, you get long-tail distributions. This is an example of a rich get richer phenomenon, and this is a common pattern in lots of systems that produce long tails. If what you get depends on what you have, the tail of that distribution tends to get longer and longer. So jump to the notebook, read the next section, which is about the Barabasi-Albert model, and stop when you get to the cumulative distributions. Okay, there are a couple of things in this section of the notebook I wanted to draw your attention to. One of them is the implementation of the BA model. This is a function that comes from NetworkX itself. So NetworkX has functions that will generate random graphs using lots of different models that people have proposed. So you can see this is just the implementation of what Barabasi and Albert described. It loops, you tell it how many nodes you want, that's n. And then you start out, when you add a new node, you're going to connect it to k other nodes. And then the random seed just means that you can get the same graph every time if you want to do that. And the loop kind of does what you would expect, which is it chooses k other nodes and adds a new node connected to them. And then it uses the repeated nodes list, is a list that has every node in it with repetitions for every edge. So if you draw a random sample, you will get each node in proportion to how many edges it has. So it's just kind of a computationally efficient way to do sampling with preferential attachment. And that is that. Now, the next part is trying to create a random graph that has the same size and structure as the observed graph. So n is just the number of nodes, m is the number of edges, and so k is the average number of edges per node. And now if I create a Barabasi-Albert graph with those values of n and k, I will get a fake synthetic random graph that is statistically similar to the actual data that I saw, and in particular, it will have roughly the same number of nodes, actually exactly the same number of nodes, about the same number of edges per node, and then the question is, have I successfully replicated the degree distribution? So when people talk about the structure of a graph, what they often mean is the distribution of degrees in the graph. And here's what they look like on a linear scale. On this scale, they look visually similar, but this is not the best way to look at them. On this scale, this is a log-log scale. And that's the original data on the left and the BA model on the right. And the question is, do we feel like this model has captured the structure of the original network? It seems like the tails are similar, qualitatively at least. Everything to the left of 10 to the 1, so people who have 10 or fewer friends, seems like this is not a good match. So this model does not describe unpopular people well, but maybe it describes the tail of the distribution, and if that's the thing we're trying to explain, then maybe that's enough for this model to do. And I'm being deliberately a little bit undecided about this. It's like many models. It's wrong, but some models are useful. So the question is, does this model help us? Does this do some work? So again, that's the data. On the face of it, clearly different. But maybe we've explained why the tail has the shape that it does. And this gets us back again to this idea of how realistic does your model have to be in order to be persuasive? And I want to make an argument. I'm going to make an affirmative argument on the behalf of Barabasi and Albert. And I'm not necessarily trying to persuade you. I'm going to lay the argument out, and you can decide whether you're persuaded or not. But the idea is that for an explanatory model, we don't necessarily need realism. We need the minimum amount of stuff to reproduce the kind of behavior that we're trying to explain. And this is related to what I said about Schelling. He's not trying to describe actual human beings. He's trying to say that this is the minimum set of stuff you need in order to produce the behavior that we're trying to explain. So in their paper, they claim that you need both growth and preferential attachment. If you have both of those things, you get a long tail. If you take away growth, you don't. If you take away preferential attachment, you don't. So their claim is that these are the two essential features that are that are sufficient to produce what we're trying to explain. They may not be necessary. There could be whole other models that don't have either of these properties that also produce long tails. And again, coming back to what I said about an argument by analogy, they're not trying to say that real people behave like this. So when you join a social network, you don't pick K people according to how popular they are. You pick your friends. But maybe your friends are more likely to be in that social network if they're popular. Or maybe you're more likely to discover them if they're popular. So there could be nudges toward this model. It doesn't have to be exactly the behavior, which suggests a different kind of argument that I'm going to call an argument by categorical membership. And we're going to say that there's this very abstract model. That's the top of this diagram. The very abstract model says any system that has these two properties, growth and preferential attachment, will yield long tails. And so if you show me a particular example like system A, if it belongs to the club, if it meets the membership requirements, if it checks off the boxes, then it is in this category and it will produce long tails. And similarly with system B could be a wildly different system that is not like A in any way, except that it also ticks off the boxes, belongs to the club, and therefore produces long tails. And this is the nature of an argument for why we might see long tails in the real world in wildly different systems. I mentioned the craters on the moon and the distribution of wealth and the sizes of earthquakes and how much damage is done in natural disasters. Those systems have nothing to do with each other. There is no argument by analogy between them. But if we see a behavior, a common behavior in all of them, maybe it's because they all belong to the long tail club, because they have these essential features. So that's the nature of the argument. That's the kind of modeling work that we're doing that is in some ways just a different kind of model for a different kind of purpose than more classical physical models of the system that tended to be differential equations and continuous mathematics. This tends to be not equations, but programs, and not continuous mathematics, but lots of discrete if-then kinds of rules and discontinuous functions. So that's my suggestion, that we have different kinds of models for different purposes, and maybe we have different criteria for what makes a good model. In classical physical modeling, we want realism. That's, in some sense, the most important thing, and simplicity is good, but not at the cost of realism. In complexity science, maybe, and I'm putting this out as a conjecture, it's the other way around. What we really want is the simplest possible system that can produce the behavior we're interested in. It can be highly abstract, and being highly abstract is actually good. Making it more realistic actually doesn't make it do more work. So if I have growth and preferential attachment and the nodes have to be red, that doesn't help because red is not an essential feature that produces long-tail distributions. It's a terrible example, but hopefully it gets the idea across. Let me pause there. That's all we're going to do with random graphs today. I want to take some questions, and then I will wrap everything up. And I will point you to some future resources. Comments? Questions? Yes?
There's classical continuous dynamical systems that do produce long tail type distributions.
Yes.
What are out there at the interface between these two approaches?
Oh, good question. So I'll repeat it just so people hear it. There are classical physical models that also produce long tails. So you don't necessarily have to go to graphs and discrete things and rule-based systems. There are also, let's say, equation-based explanations. What's the interface between those two things? I don't think I have a good answer other than, that's a great question. Thank you for asking. I repeated it, but I don't have a good answer. Other thoughts or questions? Because I did such a good job with that one. Okay. Let me give you some homework, a couple of resources. So everything that I did is from Think Complexity. If you would like to read more, it is available free from greenteapress.com. Green Tea Press is me. That's where I publish my own books. You can grab the PDF and read that there. If you would like to have a hard copy of it, the nice people at O'Reilly Media will happily sell you a copy of that. If you're interested in more of this, so if you liked the graph stuff that we just did, that's in chapter 2 of the book. And one of the other examples that's in there is the small world experiment. If you've ever heard this idea that you are separated to everyone else in the world by 6 hops in a social network, that's where that came from. That claim may or may not hold up to scrutiny, but that idea is an intriguing one. Chapter 2 is about that. If you like the game of life stuff, chapter 5 is about cellular automata and talks about Wolfram's principle of computational equivalence that I mentioned. This, by the way, is a Turing-complete cellular automaton, and it's even simpler than Game of Life. This is a one-dimensional automaton that's evolving over time, and it is Turing-complete. And it is not proven, but arguably the simplest possible system that is Turing-complete. If you like agent-based models, you might like chapters 9 and 10, which are about other agent-based models, including Boids. These are sort of like birds, moving around in 3 dimensions and following a simple set of rules. Basically says, if I'm flying beside somebody, I'm going to try to align with them. If I'm too close, I'm going to move away. And if I'm flying with a herd, I'm going to tend to move toward the center of mass. And it turns out that if all you do is follow those 3 rules, you get behavior that visually looks remarkably like flocks of birds, schools of fish, herds of animals moving. It's cool stuff. The philosophy stuff we touched on a little bit. Chapter 1, I lay out a framework for where I think complexity science is and where it's going. And I'm going to talk a little bit about that now. And then each chapter has a little bit of a philosophy section at the end. So here's my claim. We are in the middle of a scientific revolution. We just don't know it yet. Because we're down here on the ground, but in 100 years, we're going to look back and realize that that was a revolution. It's a change not in our understanding of the world, but in our understanding of science. Like, what's considered to be science? What's considered to be a good model? Things that used to be bad models are now good models, and vice versa. So here are some of the things that are changing over time, which is we are moving from equation-based models of the world to things that are often based on simulation, replacing analysis with computation, moving from continuous to discrete and also hybrid continuous discrete, moving away from linear things, looking at nonlinear things, especially discontinuous, away from away from deterministic to stochastic models, and filling in that middle space that I talked about at the beginning. Between 1 and infinity, we're working in from the boundaries toward the many part of that space. I didn't talk about this too much today, but if this is a new kind of science, we might wonder what the new kind of engineering looks like. Now, I mentioned in part the inability to isolate subsystems when they interact with each other in complex ways. And on the one hand, that makes design really hard, because that is almost the only tool we have as engineers, which is to divide and conquer. Because you have to divide, conquer, and then integrate. And if you can't integrate subcomponents, we don't know how to engineer. However, we do know how to search through design spaces. And that's what engineering might look like as we move toward complex systems, ways of understanding the world. You don't necessarily design the system that has the behavior you want. You search for a system that has the behavior that you want. And this is an example of redesigning a part by doing a genetic algorithm. The thing on the right is designed partly by human beings and also designed for manufacture. The thing on the left is what you get if you throw this into a system that does an automated kind of search for optimal designs. The interesting thing about it is, 1, it does not look like what people design, and 2, it does look like what nature designs. Question? Did I say the opposite of what I meant?
Yeah.
Okay. But you knew which one I meant. Good. There's also a new kind of thinking that gets into this, which is away from Aristotelian logic to many-valued logics, and away from frequentist probability to Bayesian probability, which is what I talked about this morning. How many people doubled up? How many people were in my Bayesian workshop this morning? Okay, you are brave souls. You have been listening to me for 8 hours today. Thank you for doing that, and I'm sorry. All right, last thing, a couple other resources I want to point you to. The Parable of the Polygons is a really nice web page where you can play around with these agent-based models. They have a shelling model, but also lots of variations and other cool models and pretty cartoons. Some of the books, if you want to read about agent-based models, that's Schelling's book. And I mentioned Sugarscape. Artificial Societies is about Sugarscape. And if you're familiar with Logo or Mitchell-Resnick, Turtles, Termites, and Traffic Jams is a nice exploration of agent-based models. Emergence, I mentioned. This is a book about emergence. All of this is in the slides. Cellular automata, this is the great whacking tome that Stephen Wolfram wrote about 15 years ago now. It's 1,000 pages long, but it's an easy read. The Barabasi Albert, Barabasi wrote a book that is about scale-free networks. This is written for a popular audience. I realize you can handle the technical stuff, but you might also enjoy the popular presentation. And finally, if you would like to get in touch with me at any time, here are 4 different ways to do that. So let me pause there, see if you have any questions or final thoughts, and then we will be done. Now, I hate to say that because it's a little bit loaded, because if you ask a question, you feel like you're making everybody stay. But let me give you a chance. Yes?
So for that mechanical part model that was generated by the computer algorithm, that doesn't seem to be very manufacturable.
Ha!
So
Right.
Can the model take into account the ease of manufacturing into the design?
It certainly could. So if ease of manufacturing is one of the constraints, then you probably wouldn't get something that looks like that. These were 3D printed. And so when you have additive manufacturing, obviously things that are very difficult to machine become printable. Yeah, no, that's a good question. And actually, I should say, the middle one is constrained to have the same attachment points. And then the third one relaxes that constraint, That opens up the design space, leads to a different solution. Question?
Is there a branch of science or engineering that's kind of further along that you would say along this quiet revolution? Or are we all kind of the same spot?
I think in the social sciences, they're using a lot of agent-based models, more so than in the natural sciences. But there are certainly examples from the natural sciences, like the Ising model, some others. But yeah, the social sciences. And in engineering, I think mechanical is one, and architecture is another. They use agent-based models as well. Those are the examples I can think of. It's probably not a very complete answer, but off the top of my head. Yeah?
You think philosophically that this might have some big impact on the great unknowns of science, like high energy physics or biology, that there may be some discreteness in the core?
Right. So do I think that this will yield, either philosophically or practically, fundamental changes in fields like physics and biology? I mean, the honest answer is I don't know. I can, for example, channel Wolfram. Wolfram has an entire section of his book that is a potential discrete model. It's actually a network model of some subatomic physics. And that is a possible explanation of physics at almost the lowest possible level in terms of discrete things, nodes and edges, and rules, evolution rules. And that is different from classical physics. In classical physics, we by and large look for continuous mathematics and differential equations. So yes, I think there will be breakthroughs, but I can't predict them. Other thoughts or questions? Yes? Is there a way to reverse it? Meaning evolve it backward in time? It's not information preserving. So from a final state, you can't get the initial state. Ooh. Aha. Could you get possible prior states in a performant way? So I'm going to say yes to the first question and no to the second. It would explode pretty quickly. The number of possible states would grow exponentially as you go back in time. At least, in general. Yeah.
I was using like a traditional machine learning algorithm to do something that use complexity science, for example, use complexity science, say the time series model, creating a future, they make you on its own,
Right. Yes. Okay. So you're talking about, you mentioned, you're doing some kind of machine learning model. Maybe you're trying to explain a time series. So particularly looking at time series data, could you use a complex system model to either make a quantitative prediction or to qualitatively explain why the time series is the way it is? Mm-hmm. Right. Yeah, let me give that one a yes and a no. So the yes is, if you're trying to explain why a time series behaves the way it does, then a complex systems model that evolves in time is a good candidate. So for example, if you're trying to explain changes in a stock price over time, people have proposed things like Brownian motion as models of that. However, what you were talking about is model fitting. So I've got a time series and I want to run a complex type of model in order to match a data set. Well, almost all model fitting works by some version of gradient descent, which is I'm going to start with a set of parameters, I'm going to run my system forward and try to figure out the derivatives that tell me how to adjust my parameters in order to fit the data. In complex system land, there are no derivatives.
I wouldn't think so, like for instance, like
Maybe.
Complex system can describe that. I don't create something alter that distribution. I just bring that say pattern. I
Right.
pattern the machine learning model, and then just wait to send out the weight of the other continuum effect to help with the complex system will form the machine learning.
Could be. I'd have to think about that. More. But in general, with complex systems, model fitting is hard because we don't have continuousness to help us. Right. Good. We'll have one more, and then we're done.
There's something about the definition of complex systems that is continuous.
No, and sorry, I shouldn't have made that quite such a black and white statement, but they tend to have discrete entities, and the rules tend to have things like if statements in them that are discontinuous, and very often, like game of life, you tweak one parameter. You take one part of your initial state and flip it from 0 to 1, and the system behaves totally different. And so in that environment, there's no concept of being close. And even if you are close, there's no direction to go in to try to fit better. So one of the examples that people use when you talk about optimization problems is it's a little bit like being in a boat on a lake and you're trying to find the deepest point. And you have the ability to drop a plumb at any point and figure out how deep it is. So if I drop a plumb here and it's deep and I go here and it's deeper, then I figure, okay, I'll keep going in that direction. But if every time I drop a plumb, I get a totally random value, or at least indistinguishable from random, I don't know what the landscape looks like. I don't know what direction to go in, and my ability to find the minimum is no better than just taking random attempts at it. So that's what the idea I was trying to get. Okay. I will stop there. Thank you all very much.